Study Unit 1, Lecture 8. This lecture focuses on triacs, which are probably the most complex thyristor device used in common practice. A triac is essentially a device which, dependent on the polarity of the pulse applied to the gate, will change the current, or rather the direction in which current conducts. The triac construction is rather complex, so in the example here, which is a triac from only one view, there are several doping regions which will, depending on the input current at the gate and the states of the voltages at M1 and M2, cause the device to behave in different ways. As shown here is doping region N4, N3 and N2. N1 is in the center, as well as doping regions P1 and P2. From the transfer characteristics shown here, it should be clear that the triac has multiple modes of operation depending on the condition of the voltages and currents at the terminals of the device. In general, or rather specifically, the triac has 4 modes of operation. Shown here is figure 331 from the reference text. The 4 modes are determined by the polarity of the current at the gate. So in modes 2 and 3, current is being sourced from the gate, and in modes 1 and 4, the gate is sourcing current, or rather sinking current, from some or other source. The modes are also determined by the polarity over the terminals M1 and M2 of the triac. So in mode 1, the gate is sinking current, and M2 is positively biased with relevant to M1. In mode 2, the gate is sourcing bias with M2 positively biased. In mode 3, the gate is once again sourcing current, but M2 is now negatively biased with respect to M1. And finally, in mode 4, the gate is sourcing current and M2 is negatively biased with reference to M1. These 4 conditions can be used to control the behavior of the triac. Once again, borrowing from the text, the 4 modes are shown here, and the current in each mode is indicated on the diagrams. In mode 1, M2 is positively biased with reference to 1, and the current is flowing into the gate. In this mode, the triac behaves as a typical silicon controlled rectifier. In mode 2, M2 is still positive relevant to M1, but a negative voltage is now applied at the gate, causing current to be sourced by the gate to the external bias. This causes junction N4 to be forward biased, and electrons are injected from N3 into P2. This causes current to flow from M2 into M1 across the junction J3. In mode 3, M1 is positive relative to M2 and a negative charge is applied to the gate. This causes current to flow from M1 to terminal M2. This happens because junction J4 is now forward biased. The forward bias at J4 means that electrons are now injected from N3 into P2. Holes are injected from P2 into N1, and this, together combined with the junction J4, causes current to flow from M1 to M2. Finally, in mode 4, M1 is again positively biased, M2 is negative, but the gate voltage is now positive. Electrons are now injected from N2 into P2. This causes junction J1 to become forward biased, and then current will flow from M1 to M2. The primary advantage of the triac, despite its complex structure, is that effectively 2 silicon controlled rectifiers can be implemented which share 2 terminals and only 1 gate. A disadvantage of triacs is that their complex structure normally leads to a non-optimal layout in silicon.